In this video, we're going to talk about flow graphs. Flow graphs are built around decision points, like if statements and while loops. They are a graphical representation of a program's cyclomatic complexity. Here's an implementation of the square root function that we introduced in the last video. Let's look at the flow of this program. First, we declare some variables. That's strictly sequential. Then we set the min and max depending on whether the value of n is less than or greater than 1. Recall that 1 was a boundary point for n. Then we have a while loop that runs until the estimate, or guess, is within the requested accuracy. Inside the while loop, we have an if statement. If the guess is within the required accuracy, we will effectively break out of the loop. If the guess is not within the required accuracy, we check if the square of the guess overshoots the original value. If so, we set the max bound to the guess and keep calculating. Otherwise, we set the min bound to the guess and keep calculating. Either way, we're going to continue iterating through the loop. Now we want to make a flow graph for this code. To do so, we'll look at 3 kinds of flow graph constructs. One for sequential code, one for conditional code, and one for iterative code. Each construct contains nodes and edges. In this construct for sequential code, we simply have 2 nodes and an edge going from one node to the next. Notice that we're not picky about the number of nodes we have here. In fact, sometimes sequential nodes are left out of the flow graph altogether because they don't contribute any information toward the cyclomatic complexity metric. Our next flow graph construct is for conditional code, or if statements. In this construct, we see 2 nodes with 2 edges going between the nodes in the same direction. One edge represents the true branch of the conditional, and one edge represents the false branch of the conditional. There is no convention regarding which edge represents which branch, just as long as both branches are represented. Finally, we have the flow graph construct for iterative code. This has 2 nodes. One of the edges from the top node goes directly to the bottom node. This edge represents what happens when the while condition is false. You break out of the loop. The other edge circles back to the top node. This edge represents what happens if the while condition is true. The code continues to iterate. Note that other flow graph constructs do exist, for switch statements, for example. But these 3 constructs here are the most fundamental and should give you a good idea of how to construct a flow graph. Now let's start the flow graph for the square root function. The code here is the portion of the square root function that directly contributes to the flow graph. Essentially, any statement that includes a condition will impact the flow graph. Let's start with the sequential code before the if statement and after the while loop. Ignoring everything else for the time being, this gives us 2 nodes connected by a single edge. We'll look at how to calculate the cyclomatic complexity metric at the end of this exercise, but it's good to know that the cyclomatic complexity for sequential code is 1, because there is exactly 1 path through the code. Now let's look at adding that first if-else statement to the code. We do this by adding 2 nodes with 2 edges between them. One edge for true and one edge for false. If we stopped here and did not include the while loop in our code, the cyclomatic complexity of this code would be 2, because there are 2 distinct paths through the code. One that chooses the true branch of the if statement, and one that chooses the false branch. Now let's add the while loop to the flow, but without adding those internal selection statements. We add the while loop by adding 2 nodes and 2 edges. One edge goes to the next node, and the other edge circles back to the node it started from. Now let's add the outermost if statement from that loop. Since the if statement is inside the loop, it gets added to the looping edge. the one that circles back on itself. When we add the next if statement, we simply pick one of the edges of the if statement we just added to represent the else edge and add the if statement to that. So that represents the inner if statement. Now we have a completed flow graph for the square root function. And now we can calculate cyclomatic complexity of the method. As it turns out, there are a few different ways you can calculate the cyclomatic complexity from just looking at the flow graph. First, you can simply count the number of predicate nodes. These correspond to conditions in the code, and add 1. Predicate nodes are nodes that have 2 outgoing edges instead of just 1. The nice thing about this way of calculating the cyclomatic complexity is that you can simply look at the code and get this number. Just count the number of conditions in your code and add 1 to it. For example, in this code, there are 3 conditions coming from an if statement and 1 condition coming from a while loop. That makes 4 conditions. And each of those conditions, by the way, is represented with a predicate node in the graph. Add 1 to this number and you get a cyclomatic complexity of 5. Next, you can count the number of regions in your graph. Here there are 5 regions. One region is in the space created by that first if statement. The while loop contains 3 separate regions. And there's a region that surrounds the entire graph. So don't forget to count the surrounding region as a region. The final method is to count the number of edges, subtract the number of nodes, and add 2 to the result. I'll let you do this as an exercise, but you should come up with 5. By now, you should realize, based on our discussion of paths and path coverage in the previous section, that cyclomatic complexity does not correspond to the total number of paths in a program. In fact, it corresponds closely to the branches and branch coverage.